So this is the last differentiation technique we'll discuss. However, we're going to apply this rule to other types of functions. So we are still going to talk more about derivatives next week. Next week, I'll talk about derivatives of log and exponential functions. If you forgot your log properties, I'll do a refresher of logs and the graphs of logs and exponential functions. I'll do that as well because we do need to do that. I also want to talk about curve sketching, like how to actually draw curves more accurately, like to find like the high points, low points. Something called concavity. I want to talk about that. This will be a pretty short unit, I'd say. I can't do too much more because I don't want to encroach on what BC does. But I do. But you're going to get a good taste of the chapter 4 in the calculus textbook and a little bit of application of the derivative. So those are things we'll do. And of course, we do have Spirit Week coming up. I am planning on testing during Spirit Week, but we can negotiate a little bit. We see next week is tricky because it's a short week. The week after is a longer week, but I don't know. Let's look at the calendar because the calendar is kind of funky for Spirit Week because C and G periods are pretty far apart. So we could talk next week. We can you guys can try to twist my arm a little bit.
It's a shorter unit.
Shorter unit, yeah. So it'll be a shorter test. Yeah. Um, but I'm also not against or averse to an alternative way of assessing this. So I'm not sure how that would look, but I don't know. It's just if we had like applications of the derivative, I totally do a project. Like there's some application involved something called related rates where you look at how like it's like totally like a physics type of situation where how things are moving in relation to each other. There's optimization. I think your mom just done that. Like you saw those projects. Yeah, those are cool things to do. The problem is that does encroach into the BC curriculum. I don't want to do that necessarily. So yeah, I don't know. We'll think about it. Anyhow, so far we know dy over dx, that means derivative. Say you're given y equals x cubed. You know what to do, right? It's pretty easy. You know that's 3x squared, right? This we already know. However, what if you want to find a derivative of this, or this, or this? These are a little more complicated functions, right? Because they're composites. Like x5 is inside of a cubic function. Sine x is inside of a cubic function. X to the fifth plus 2 is inside a cubic function. Well, if you consider y equals x to 5, then raised to the third, someone might think, oh, let's just move that 3 to the front and drop this by 1, right? Someone might think that dy over dx equals this. But is that true? Because if I just use my basic knowledge of exponents, like from like 3 or 4 years ago, before you do a derivative, that's x what power? And if I do my power rule, what do I get? Right. So these are not the same. Those are not equal. So this is not true. Fine. Then forget about getting creative here and like moving the 3 to the front, dropping it by 1. Let's just expand x to the fifth, raise to the third power, and just do it. But let's take a look at this guy here. You have y equals x to the fifth plus 2 inside parentheses, then raise to the third power. Okay. Find the derivative. Well, we know this is not true anymore. You can't just move that 3 to the front, drop the exponent by 1. It just doesn't work. Before we get too carried away with this new technique, which I'll show you because you don't know what the new technique is yet, let's expand it and see what happens. So kind of by self-discovery, we'll come up with the rule. So if I just expand it right now, y equals x to the fifth plus 2, x to the fifth plus 2, x to the fifth plus 2. So let's expand first. Now, if you expand, you can do a couple things. You can FOIL the first two and then multiply to the last expression. Or you could use this right here. Do you guys remember what this is?
No row cubes.
Yeah, there's something called Pascal's triangle. Have you guys seen this before? I think Mr. Band probably talked about it with you guys. No? I gotta have a conversation with him. See, okay, yeah, you guys already talked about it. Avery, thank you. I'm pretty sure you talked about it. Okay. Or binomial expansion or binomial theorem. There's all these different ways you could look at it. It's up to you how you want to expand it. I'm just going to kind of just go old school and just do this. X10 plus 4x5 plus 4. Keep expanding. You should get x to the 15 plus 2x10 plus 4x10 plus 8x5 plus 4x5 plus 8. Clean it up. Okay, that's pretty easy at this point, right? 15x4, 14 plus 60x9 plus 60x4, and the 8 just goes away. So does that make sense? We get that? Now, I don't think you guys want to do this consistently, especially when you get to some more, even more complicated functions that involve trigonometry, logarithms, exponents, or what if that was raised to the eighth power? And what if this is like a cube root inside? Like cube root and then minus one. Like, what if you have some really weird stuff, right? We need another technique that's more efficient than this. This is not terribly efficient. That's what the chain rule is all about. And we're going to do this again, doing the chain rule. I think on the next page we do it again. Actually, I'll do it again right now with this. I'll talk about the new rule right now with you guys, and then I'll explain what the rule is. So let me show you the new rule. This is the new technique we're going to do, and you'll see why it works. So this is one way you could do it. So we'll just do off to the margin here. So this is our new technique. And the way it works, I like to think like this. Derivative of outside times derivative of inside. So what does that exactly mean? So I'm dealing with this still, right? Y equals x to the fifth plus 2 cubed. So here's what's going to happen. We'll take our derivative. The 3 will go to the front. So I think this is the outside, because 3 is outside, right? And I'm going to drop the exponent by 1. Times, now, what's my inside? X to the fifth plus 2 right now, but what's the derivative of that? Right, what Charlie just said. 5x to the 4. So if I clean it up, it looks like this. 15 x4 x5 plus 2 squared. And you can circle that, leave that as your answer. So that would be my derivative. Now, is it the same as what I circled in blue? Or I wrote in blue? It is. These will be the same. If you kind of think about it, if you expand x plus 2 squared, right? And multiply inside 15x4, you will get the same thing. You will get the same thing. You don't have to do that, by the way. You can leave your answer like that. But just to prove to you, it's the same as in blue, 15x4, x10, plus 4x5, plus 4. We know this already, right? If I distribute, do I get the same thing? Do you get the same thing, right? So there you go. So this is the new rule called the chain rule. we call it chain rule because like this chain, I don't say chain reaction, but it's kind of like this like long stretch of things we do, right? That kind of like they all link up. In case no one noticed, chain bracelet. Chain. I didn't put that. That's from like my previous colleague. Yeah. It was done for a reason. Okay. So here's the chain rule. I think it's a little confusing the way it's written here. I don't like this. Some people look at this and I was like, whoa, this looks so crazy. This is what it's saying. It's a composite function, right? That's what it is. So think of this as your outside. Think of this as your inside. So when you say f of u, you're doing f of g. It's really f of g of x. And really, you're doing this. F prime g of x times g prime of x. That's a chain rule, guys. That's it. So the whole U business, I think, is just a little confusing. I'm not a big fan of it, but I just put it there for formality purposes. So I don't try to teach it that way. Um, so you guys remember that reference sheet that I gave you guys, right? If I go back to that, I do put that in there. I have it crossed off, obviously, so that you guys weren't confused. So I'll give you guys a fresh one that's not crossed off. Not today, but sometime soon. But you can see here, it says here, so you have f of g of x, the derivative on the outside. So f prime g of x times g prime of x, we're derivative outside to the derivative inside. Very important though, we do the derivative outside, keep that inside intact. Keep that inside intact and do the derivative outside. So I remember I had the x squared, or sorry, x to the fifth plus 2 raised to the third power, move 3 to the front, draw the exponent by 1. I kept the x to the fifth plus 2 intact. And then did times derivative the outside afterwards. So, oh, geez. Well, here we go. Oh, what did I just do? Okay, let's close that. All right, so let's look at this again. Oh, I already this for you. So let's go to example one. Okay. So example one. Here's what we do. Y prime. Move that 5 to the front. Keep the inside intact. Do not change it. Drop the exponent by 1 and multiply by the derivative of the inside. What's the derivative of the inside? Yeah, totally, 100%. And you know what? Leave it alone. Don't do anything with that. Don't expand it. If you want, no, do you want to expand the original and do the derivative of each one individually? No. That'd be crazy. You're gonna FOIL that 5 times? I don't think so, right? This would be better. Better this way. And by the way, when we start doing applications of the derivative, we do need to take the derivative set equal to 0 and like do stuff with that. Well, now you have a way to find the derivative pretty quickly. And by the way, what will give me how would I find my horizontal tangents for this equation here? What would now my derivative, right? We have horizontal tangents, your derivative equals what? So I can set this equals 0 and solve for x pretty easily. Why? Because this is factored, right? I can set that green to 0 and solve for x. I can set this to 0 and solve for x, right? It becomes easier to do that, right? And why do I care about the horizontal tangents? What happens to horizontal tangents when you have a polynomial function? The highs and the extreme, exactly, highs and lows, right? So ultimately, we're going to start graphing this. 4x cubed plus 5x squared raised to the fifth power. I'm going to start having you graph that with high level of accuracy without a calculator. You will get to that point where we can do that. But we need techniques to help us with that before we get there. Now, let's look at example two. And by the way, you can check your work in the calculator. We know this now, or even Desmos too. Just do d dx of the original equation. graph what you got by hand, see if the graphs are the same. So example two, now this is a little weird, cosine 5x, fine. Okay, y prime, what's your cosine? Negative sine 5x. You see, you guys worry, I'm not gonna have this memorized. You guys just told me right away. You guys don't need a reference sheet. Okay, let's strip the inside. 5. There you go. Because that's your inside. So you can rewrite as negative 5 sine 5x. By the way, coming back to example one again, one thing I just want to have you guys present to, f of g of x. If you compare the original equation, example one, to f of g of x, what would be your g of x? 4x cubed plus 5x squared, right? Sorry, I'm like squeezing that in. What's your f of x? X to the fifth. You see how the 4x cubed plus 5x squared is thrown into x to the fifth, right? So when I take the derivative, it's 5 whatever raised to the 4 power times the derivative of g of x, or times g prime. So you see how that works. Likewise here, your 5x is the inside, your 5x is the inside, your cosine is the outside. Okay, let's look again at example 3. Okay, yeah, this is what I really like. That definition, that's how I want you to think of it. The derivative of the outside, keep the inside intact, times the derivative of the inside. This is precisely chain rule right here. That's it. You know that really well. And guess what? There's 21 questions on the next at the end of this packet of the worksheet. I'll look at. I think we'll see how far we get today. I might have to taper that. I might have to assign fewer problems because 21's a lot to do. Here, y prime. What do I do, guys? Where's the 3 go? Front. Keep the inside intact. Drop the exponent by 1 times. Now I'm color coding, kind of a bit of contrast. Now, careful here. Root x is x to the half. So that's 1/2 times x to the negative half. And 1 over x is x to the negative 1. So it's negative 1, x to negative 2. Technically, we are done, but it's usually nice to avoid negative exponents and to use radical form if you can. So 3 parentheses root x plus 1 over x squared times 1 over 2 root x minus 1 over x squared. So that's just a little cleaner, I suppose. Okay, so this is our new technique, chain rule. Questions? Yep, okay. I will be honest, it's a pretty dry and boring topic, but this is something we need to have the skill for all the stuff we do down the road in calculus. It's one of the most important rules we do. Okay, let's try it again. Y prime equals, what's your sign? Cosine. Keep the inside intact. Times, what's the inside? 7. Plus, what's the tangent? Secant squared. Keep the inside intact. Drew the inside. 6x. Leave it alone. It's all good. Most of your homework or like test question like this is just gonna be one line. Just kind of one line. Just make sure everything's done correctly. If you want to put the 7 in front of the cosine, 6x in front of the secant squared, I don't care. It's up to you. Okay, let's try more. Okay, example 5. Cosecant cotan. You guys remember the derivative of cosecant? Yeah. It's a little tricky because you're gonna have to do this. and then times, let's do a cotangent.
Negative cosecant squared x.
Correct. But inside, I have to keep the inside intact. And there's nothing else I can do about it. I can't combine the negative cosecant cotan x with negative cosecant squared x because their inputs are different. So I just leave it alone. Leave it alone. Don't touch it.
Wait, why do you have to split it into two again?
Because you have a composite function. You have cosecant cotangent x. My outside's cosecant, so I focus on that. Then I did times derivative of the inside, which was derivative cotangent negative cosecant squared x.
Oh, okay.
So this is where Albert IO will be tremendously helpful because you're going through multiple choice. You guys kind of need to drill and kill with this. And the homework you look at, it is like a lot of drill and kill. But Albert IO will be really good too because it does clean it up a little bit. So then you know kind of where to stop. So I'll make sure we have that next week. And I'm thinking about doing a quiz on Thursday next week. I'll let you guys know for sure by Tuesday. But because we're gonna do more of this on Tuesday as well. Example 6. R equals sine squared theta. Who cares? R, theta, y, x, it's all the same. It's not a big deal. It's just, but one thing to keep in mind, if you see sine squared x, hopefully you guys know it's sine x then squared. Or if you see cosine raised to negative 3x, sorry, cosine at negative 3x, it's like cosine x raised to negative 3. Make sure you're aware of that. And notation wise, make sure you know that like something like that's like the same. But are those the same? What does that represent? Yeah. And we won't do inverse derivatives in this class. And it is probably the most challenging of all the derivatives you'll do. It Ms. York and I have a really good way of teaching it, but we'll push that to the fall when you're in BC. But just so you know, that is inverse sine. Don't confuse that. What's this going to be? 1 over sine x. Yeah, just make sure you're aware of that. Okay, let's look at example 6. So r prime is 2. Actually, before I get too carried away, let's write that first. Now let's do a derivative. 2 sine theta raised to the 1 power. And what's the derivative sign? Yeah, and by the way, you don't have to write the 1 power. So you just do that. By the way, that's sine 2 theta. Okay, in case you guys are curious. Also remember, this is a polar. It's a polar function. The one thing that differentiates this class, no pun intended. You guys got that?
Mhm.
Yeah, I see. Play words. Okay, cut you guys awake. That distinguishes this class from AB. You guys have to derive polar curves, and you will be working heavily with polar curves in BC. I'm not going to worry about that per se, like the graphing of polar stuff, but just keep in mind that that does come back. Um, but yeah, that's R prime for example 6. Okay, this is where chain rule can get really dicey. You might have to do chain rule multiple times. So you may have like a composite of 3 functions or 4 functions. You can do a triple chain. That's kind of crazy. But we'll focus on double chain for example 5. Now for example 7, this is going to be product rule and chain rule. Now here's the deal. Can I distribute that x to the 5th right now into 7 minus 2x raised to the 6th power? No. How come you cannot? What fundamental rule from like day 1 of math?
PEMDAS.
PEMDAS. Thank you, Charlie. You can't because of PEMDAS. You have to take care of x parentheses for exponents, right? You can't. So you could expand if you wanted to and FOIL it 6 times and then distribute x5 and then do the power rule. That'd be crazy. Don't do that. Here's what I'll do. You need to be very organized in this approach. let's call this F, and let's call this G. So what's Y prime going to be? F prime G. We're cool with that? But G prime, is G prime a simple derivative? Not really. G prime requires what? The chain rule. So let's do it off to the side. If we do it off to the side, you have 6, 7 minus 2x raised to what power? And what's the derivative of the inside?
Um,
Right. If we clean it up just a tad, that might be a good idea. Okay. So now let's come back here. Y prime is going to be F prime. F prime is yes, 5x4. G is easy. That's 7 minus 2x raised to the 6th power. Plus F, which is x5. And then 7 minus 2x. Oh, but it's negative 12 times 7 minus 2x raised to the 5th power. Ah, come on. And if you wanted to clean it up just a little bit, I could factor out x to the 4 and factor out 7 minus 2x raised to the 5th power. If it's multiple choice, it probably would show that. And then what's left behind? 5 minus 12x. Sorry. 5, 7 minus 2x minus 12x. And you can clean up just a tad more. Ugh. 35 minus 22x, I think. Is that right? Yeah. So you see it's a very, very mechanical process, right? And sometimes it's advantageous to do that. Because what if I asked you, where's the horizontal tangent to this, right? Then you have to have it in fact form, set equals 0 solve for x, right? So yeah, that kind of was a good idea to do that. So F prime, you see that's 5x4. G, of course, to keep it intact, that's multiplied by 5x4. Then plus the reverse, F versus x5, then G punched it off to the side, brought back into the fold. When I worked that out, I realized, okay, I have this now, x to the 5 times negative 12 7 minus 2x raised to the 5th power. And then this is the part that might be a little tricky. This may not be crystal clear. So let me get a highlighter. Notice that both these have what in common? X to the 4. So that's 4 got pulled out. 7 minus 2x to the 6, 7 minus 2x raised to the 5th. What does that have in common? 7 to the 5th. So all that crazy factoring we made you guys do last year or in middle school, now you know why. Now you know why we care about that. Because we want to make sure you guys are comfortable with the factoring process. So you have these crazy polynomials happening here, but we factor out from both of these groups. There's two groups plus in the middle, right? And then inside the brackets, there's a 5 left over and 7 minus 2x, and there's a negative 12x left over. And if you clean it up with ink, you get that. I factored. So what I did was after I did the product rule and I did the chain rule for the G prime, I decided to go a bit further and clean this up by highlighting these two groups separately, realizing, oh, we have some stuff in common. And I pulled them out. And inside the brackets, I saw what's left behind, clean that up even further. So this enables me, if I want to find horizontal tangents for this, I know this will happen at 0 for sure. It'll happen at 7/2 for sure. And it'll happen at 35/22 for sure. So now I know where my horizontal tangent is coming. And by the way, you can do a sine chart too, right? Well, you can do a sine chart for this and kind of see, oh yeah, okay, this is where it was all happening. So this would be a nice extension um, to do curve sketching. Maybe not next week, but probably the week after, right before Spirit Week. Would be good to do that. Um, okay, this is where even more fun begins. Okay, and let me just pace myself appropriately. Okay, I don't care about that last page. That I could save for next week. That's just more. This kind of explains to you why we have to think. Why when you do derivative of trig functions, you have to be in radian mode. I could save that for next week, but I do want to do example 8, and I think I can squeeze in the last page as well. The last page I love. These are my favorite problems because you actually have to know the rule really well to do this stuff. And I didn't ask questions like this on our last test. I will on this upcoming test. Example 9, you may want to write a circle. That is definitely a test question. So is example 8 too. I love both those questions. Okay, this is what we call a double chain. This is a double chain. So here's how it's going to go. Okay, this is my favorite. This is the one time you get to pull this guy out. Okay, and this is from Giants. Yeah, that steroids. Famous player for Giants 20 years ago, retired. Barry Bonds. This is what Barry Bonds is?
No, what about Barry Bonds?
Okay, good. Okay, anyway, I got this from a promotion from a one of the Giants games many years ago, right? Okay, do you know what this ball's called? So which ball, yeah, it's a Russian ball. Okay, and there's nothing you can pick. So this is pre-steroids, so these are college. Barry Bonds is very skinny. Then joined the Pirates, Hall of Famer Pirates, and then when the Giants got really big, right? Yeah, think of this as H of S. This is H of S. This is the inside. He goes inside the Pirates. He graduated from Roll Technology graduated. Got drafted by the Pirates, plays with the Pirates, right? In the late 80s, early 90s. Okay. This right here is G of S. Then he gets signed by the Giants and does steroids and it's a lot of
It's all home run.
It's a lot of home runs. But it's not fast. He's far from homeless. He's very wealthy. But he cheated. Steroids.
Oh,
Yeah, yeah.
You think it's cheating if everybody's cheating?
Oh, A-Rod's on Hall of Fame, Clem's on Hall of Fame. There's a lot of guys on Hall of Fame. What was that? I don't say he's fat, but I mean, he got like much. I'll show you some photos if I can find. Like he got much bigger later in his life. A 40-year-old, some of their 40s, it was like late 30s, late 40s, not beginning. Not be breaking major league records in home runs. So it's seriously going on.
he's supposed to be not, he's too old.
Well, now he's retired now. But anyway, point being, I digress. I love baseball. So this is alphabets. So F, G, 8. So think like that. If you want a visual, right? So here's what's going to happen. X squared minus 5. That's in your H. Cos that's in your G. Sine that's in your F. So Barry Bonds, Arizona State is for Pirates, San Francisco Giants. Inside, outside. So here's how it's going to go. Y prime. Okay, what's the derivative sine, guys? So cosine, bracket, and I'm going to keep the rest intact. And remember, my f is going to be sine x. My g is going to be cosine x. And my h is going to be x squared minus pi. Okay, but I'm not done yet. Very far from done. See this? Make a little more space here. Okay, times. Now I got to do the derivative of cosine. And by the way, Here's how this row is going to go. My apologies, I didn't write this out earlier. F prime of g of h of x times g prime of h of x times h prime of x. So sorry I didn't say it earlier because that's important. So I'm doing f prime, but keeping g of h of x intact. Derivative sine as cosine, so there you go. Now what's the derivative cosine? So we're going to do negative sine and keep the inside intact. And finally, what's the derivative of x squared minus pi? 2x. And that's going to be your derivative. So keep the outside, do the derivative of the outside, keep the rest intact. Derivative sine is cosine. Then you do the intermediate, which is negative sine, but keep its inside intact. Then multiply by the derivative inside. So it's kind of like, Bonds of the Giants, Pirates, Arizona State. So that's f of g of h of x. I could add a fourth function. That's going to be kind of crazy. That's a little much. That's called triple chain. We call this a double chain. So it's a repeated chain. And I'll make sure you guys practice this. This takes practice. So you'll need to practice often. Okay, questions? All right, let's move on to the last page. No, page 4. That's what I meant. Page 4. So look what we have here. We have f prime of all these different values, g prime of all these different values, and we have a bunch of different parts here. Let me tee up A and B for you guys and have you guys try and see what you get. So I'm looking for a numerical answer. Look for a numerical answer. So if I tee this up for you guys, I'll have 1/2. I'll do a bracket. F of 5 times g prime of 5 plus f prime of 5 times g of 5. For B, this is chain rule. F prime of g of 5 times g prime of 5. And for C, it's cubed, so it's going to be 3 g of 5 squared times g prime of 5. Because what's happening here is that you have g of x, you do 3 to the front, dot x front by 1, multiplied by the inside. Go ahead and compute each of these three. You have all the information about them. Don't try to do it. And I'll pull up the answer key and kind of slowly show the answers. Ah, she got a little lazy there, didn't she? Um, You guys get -13? Pardon? Okay, cool. Okay, good. All right. Keep going. -13 makes sense for that one.
Oh, there it is, I can see.
I'll have you guys do the odds for the homework. Doing 21 questions over the weekend. It's a little brutal. We'll do 1 to 21 odd for the homework, just so you know. Do all of them. Do all of it. Okay. I think it's cool because there's this bit of certainty with this. Like you're looking for a number. Okay, for part B, you should be getting -10. Yeah, because f prime of g of 5, g of 5 was 2. No, g of 5 was 7. F prime of 7 is -1. And g prime of 5 is 10. So you get -10 for B. So B should be -10. Yeah, I didn't ask these questions on our last test because we didn't do chain rules, so I didn't feel like we were ready for that. But now I have more options, more flexibility here. How about C? Should be 1470. It's 1470 because you move the 3 to the front, drop the exponent by 1, multiply to the inside. G of 5, of course, is 7 squared, you get 49. Times 3, what's 147? G prime 5 is 10, you get 1470. And by the way, sometimes we use these little symbols here to show how many times this function's happening, just so you know, if you have that, if you likewise with derivatives. And just for good measure, for D, you can write it as you don't have to do a quotient rule, by the way. You could if you want. You can do a quotient rule for part D. But if you write f of x raised to -1 power and use the chain rule, move -1 to the front, drop the exponent by 1, multiply to the inside, and work it all out, you get -1/8. If you want to do quotient rule, go for it. You totally get the same answer. By the way, you never ever have to use quotient rule if you don't want to. If you really don't want to, just make the bottom raised to -1 and do a product rule with it. You always can. You never have to do quotient rule if you don't want to. Sometimes you're kind of forced to do it if you have a quotient rule with this kind of situation. It just depends on the way the problem's written. Last thing I want to say before we end for today. What I wrote here on the board in blue, x cubed. We know it's 3x squared, right? But you've been doing the chain rule the whole time. Not realized it. Move the exponent to the front, drop the exponent by 1. When you multiply to the inside, let's do it back straight up. So you've been doing it all the whole time. Not realized. So hope that makes a little sense. Okay, homework. I'm just gonna have you guys do, yeah, just 1 to 21 odd. I do want to do the odds because I want you guys to do some trig also. So 1 to 21 odd, and then maybe we could do the evens during class on Tuesday. And we'll kind of talk about the calculus stuff as well. And maybe I might introduce log exponential derivatives. I'll see if they have a chance to do that. But yeah, we're all set. Okay, we're all done. No problem.